of thing. All right, so questions. PA2 is due tomorrow morning, 8 o'clock. This is a perfect time to ask those final questions. Okay, so submitting PA2. So let's suppose that you're making a single file, and let's just suppose it's called stick.c. Okay, so you compile it the usual way, you test it, everything's good to go. This is the file that needs to be submitted to me, okay, not the executable. So do the following, tar cvf, and then the name of an archive, and don't call it stick, okay, because there's just a chance of bad things happening. So call it something like pa2.tar, but make sure it's a .tar, and then list whatever file you want to upload. If you've broken your file into multiple pieces, stick.c, start.c, pick.c, you can name all of those here, and they'll all go into pa2.tar. Say again?
Can you include a header file?
And a header file, yeah. All right, so that's the first step. Go ahead and make this tar file, and then you want to compress that. So gzip pa2.tar, and that will create a pa2.tar.gz, and then rename that. So move pa2.tar.gz to pa2.tgz. And probably your first step, right, copy. Actually, no. After you do that, all right, copy pa2.tgz to your machine, and then upload to Canvas. So copy, you can use WinSCP. If you're on Windows, you can use SFTP. If you're on Linux.
What is that second line start with?
Which second line? gzip?
Gzip.
Yeah.
Can you also show us to unzip it?
Yeah. And these are all spelled out in PA1's instructions. But to unzip, okay, here's what I would do. Make yourself a totally new directory. Okay, make dir new area or whatever you want to call it. Something that doesn't have any files in it to begin with. Okay. Copy whatever your TGZ file is into that new area. Right, so download from Canvas and push it up to the Linux server. Copy that into a new area. Change your directory to that new area. And then unzip pa2.tgz, and then tar xvf pa2.tar.
What does the XVF mean?
Extract, be verbose, and here's the file name of the archive. So CVF creates a file, TVF shows you the table of contents of a file, XVF extracts from a file. And then GCC-O, the usual thing to build an executable and then execute your program. And you got to do this in a new area, because if you do this in the area where you've developed your code and something goes wrong in here, you might not actually be dealing with the archive at all. You might just be dealing with a file that's already sitting there. Or something might go wrong in here and you might clobber the file that you've written because it was stored in here, but it's a different copy of it or something. So make a new area, right? Directories are free, right? You can do everything in its own directory, and it's not a bad policy. All right, so that's how you can unzip. But it's basically the same way you submitted PA1, and everybody was able to do PA1 submission, so I'm expecting PA2 will go fine. So questions on the program itself? Everybody good with all the scanf, fgets, that kind of stuff?
Should we be containing our messages to standard out or standard?
Just do standard out.
And should we return -1 if there's no?
Don't have to, but you're welcome to. I don't automate the grading of these, I do them by hand, so. But sometimes if there's a lot of output, I put it through more, and if you print the standard error, it'll come out somewhere else. So that gets a little confusing. So how do you tell if this found a valid integer or found something that was not a valid integer?
Valid integer registers as 1 always.
Right, the return value from scanf will be 1 if it's a valid integer. And it will be different from 1 if it's not. You can't look at this and know whether it saw a valid integer or not, because it does not change the value of this. So the only way to know if this thing actually found an int was to look at the return value. And if it does, then that's the value that it converted it to. And should this ever be the first line of your program? Why not?
Never mind. I didn't put the never mind.
I just have a question. So with scanf, I made a global variable for like the integer or the number of sticks left, and I couldn't store that. I couldn't scanf that into the global variable. It just kept on giving me a segmentation fault.
Should work. How did you make your global?
I just declared it on top or above the int main program.
And you just said int number of sticks semicolon?
What I ended up having to do, I just had to store scanf into a different variable and then just made global into that variable.
Show me your code later, because that should work fine. As long as you put the address of the variable here, it shouldn't matter if it's global or local. In general, though, we're going to try to avoid globals for the most part, because you can always pass that variable to other routines, right? And you can pass it back. Globals make life easier sometimes, right? Because you can just set the value somewhere. But in general, we're going to try to avoid them. But if it works, that's good. So why can't this be the first statement in your main program?
You have to check RC.
Got to check argc, right? If you come in here and you try to work with argv bracket 1 and they ran the program without any arguments, this will seg fault, right? And the only way you can prevent that is by first checking to see what argc is. If argc is at least 2, then you're safe doing this. But if argc happen to be only 1 and you do the scanf or you do a printf or anything else with argv bracket 1, you'll probably seg fault. So those are probably the two main things I see with scanf: not checking argc before you use argv and not looking at the return value from it. All right, gone. Cool. All right, so let's talk about GDB. Let's talk about debugging. So debugging is the process of you've written your program, you have somewhere on paper in your head something, an algorithm in mind for how this program should work, and the final result should be such and such, and you run your program and either it doesn't give you the right result, or it runs forever and never gives you any result at all, or it seg faults and exits prematurely, or something is going wrong, right? And the question is, how do you reconcile the difference between what your algorithm should be doing and what the code seems to actually be doing? And so what do you typically do when when you get into this situation, you've written your program that should play the matchstick game, and you run it and either it seg faults or it's always picking one stick, or it picks sticks forever and the game never ends. How do you go about debugging that?
Use printf statements to check.
Number one go-to, right? Put in printf statements, because that will tell you where you are in your program, and it can tell you the value of variables in your program. So if your number of sticks is never changing, right? Every time that you think you're changing the number of sticks, put a print statement before current number of sticks is such and such, and then right after say new number of sticks is such and such. And there's a good chance that those print statements will never appear. And that's going to tell you I'm never getting to this section of my code, right? So you got something in the flow of your program. Or maybe it says current number is 12, new number is 9. Well, I set the sticks to 9, why did they go back to 12, right? So now you go through your code and you look for every place where you assign a value to number of sticks, and you find somewhere where you set it equal to the original number instead of something else, right? So printfs are sort of the number one go-to, right? Figure out where you are in the code and look at the values of variables. You can also stare at your code for hours and hope that you see what the problem is. And sometimes that works, but not usually. It's usually not a lot of fun, at least. Sometimes you sit there and you play computer, right? You write out the values of each variable on paper, and you step through your code and you write down the new values as things change. And that can help if you think there's a problem with the algorithm, right? But that's really just kind of doing the print statements without using the computer. And sometimes you delete the file and you start writing it from scratch, right? It's like a purification ritual. That can be helpful, but takes a lot of time. And if there's a conceptual error, you're probably going to repeat it in the next version. So a debugger, like GDB, is a tool that will basically let us do what we do with print statements without having to go in and add a bunch of print statements. So GDB is the GNU debugger. It's available on pretty much every Unix system. And it understands C. It understands assembly language. It understands a lot of different environments. And we can use it to basically run through our program and either step one line at a time, right? And it will show us our source code as it's stepping through. And we can examine the values of variables. We can change the values of variables. We can set what are called breakpoints, which say go ahead and run until you get to this line of code and then stop. And every time it stops, it basically comes back to us and it gives us a prompt and says, what do you want to do? And we can say, show me the value of this variable, execute the next line of code, show me the source code, things like that. So it's an interactive tool that lets us analyze how the program is executing. So before we can use GDB with a program, we need to recompile our code with a certain switch that says go ahead and include debugging information, because GDB is going to let us look at our original program in C. It's going to let us look at our comments, all of this stuff. In an actual executable, all that stuff is gone, right? When you compile C code, your comments disappear, your variable names disappear. It becomes just a bunch of machine code. So to make debugging useful, we can put in a switch when we compile, which says keep all of that symbolic information intact. And you only need one switch, and that's the -G switch. So here's how we're typically going to compile. And I'll just use stick and stick.c as an example. So somewhere in here, put in a -G switch that says include debugging information. And we could have put that here. I think we could put it here. But don't put it here, because -O has to be followed by the output file. So this would create an executable called stick, but it includes debugging information. And then when we want to debug, we say GDB and the name of our program. All right, so let's do some debugging. So I've written a program here, which is a bubble sort. So I prototype it up at the top. Sort takes 2 arguments, an array of integers and the number of integers in that array, the size, right, of things that we want to sort. And I have a main program. I've got a data array of 100 integers. I've got my usual character string that I call buffer and some other integers. And I just have a loop here which says enter a number, does an fgets, does an scanf to convert it to an integer, stores it in my array, and as long as it was a valid integer, counts that as another number and increments size. I'll talk about null in a second. So this is just a loop that builds up an array of integers. And size is the number of things in that array. And then it calls sort, which should sort this data from smallest to largest, and then I just have a for loop that prints out my sorted data. So to run this, I can put in a bunch of data, and I can hit Control D when I'm done, and it'll sort it and print it out in sorted order. So my sort routine is an inefficient bubble sort, and we'll talk about sorts a lot in 222. We'll learn several different kinds of sorts, but bubble sort is sort of the first one you learn. Do you do bubble sorts in 121? Okay. So so basically go through the whole array from start to finish and do that once for each number in the array, and basically compare each number to the number after it. And if they're out of order, then swap those 2 numbers. So this is just standard 3-line swap code. Save the value of the first number, set the first equal to the second, set the second equal to the saved first. Switch them around. Very inefficient because I go through it, you know, len times, but it's a sort routine. So I just threw this together this morning as something that we can debug in GDB. Let me talk about this for a moment. So we know we can use fgets to read a line of input from the user, right? Sometimes you want a way for the user to be able to signify that they're done putting in input. And usually the way we signal that in Unix is Control D, okay, which we interpret as saying end of file or end of input. And fgets actually returns a value to us. Okay, fgets actually returns a car pointer. And if you read the description, okay, so fgets returns a pointer to the characters that you read if it's successful. But if there's an error or if it hits the end of file, it returns this symbol null, uppercase. Okay, it's a special value. It's basically a pointer to 0. So what you can do in code is you can basically look at the return value from fgets to see if it's equal to null. And if it is, you know the user hit Control D, or the file you were reading from reached the end of the file, and there's no more numbers or data available. So a typical while loop for doing input is something like this. Call fgets, look at the return value, and if it's not equal to null, do whatever you want to do with that input, and then come back up and do another input. And at the point where you hit end of file, fgets will return null, and this loop will exit. So when I run this, the emergency drill. Is that the end of it? Whoa, we survived. All right.
It says all clear.
Okay. You know, I thought I heard something a few minutes ago, but
That was too
Oh, I think
short.
that was my,
The only thing
I
that
got
shook
an
was
email that the drill started.
oh really? Okay.
That was 4 minutes ago.
Yeah. Okay.
Alright.
Yeah, we're
All right. Well, yeah.
We survived without any
Yay.
whatsoever.
Well, this is why they do the drills, because now they know they've got a problem with their alert system. All right, so I'll give them feedback for that. All right, so if I'm entering numbers from here and I'm done with my data, I can hold down Control and hit D, right? And my code will pick that up because when I hit Control D, fgets returns a null.
Why does that guts return a null for control D?
It's just what it does. Right, it's written that way. So when you hit a Control D at the beginning of a line and you're inputting, right, standard in considers that to be the end of the file that it's reading from, the end of input. And fgets is set up so that when it's trying to read from some source and it hits the end of the file, it will return a null. So we can also I can make a file here, right, called data, and if I redirect standard in to come from this file, it will read those 6 lines of input, and then when it tries to read the 7th line, there is no 7th line, it'll say that's the end of the file, and fgets will return a null. And so this will work exactly like hitting a Control D at the end. And if my Control D is not in the very beginning of a line, right, if I type some spaces and hit a Control D, it doesn't notice it. If I hit 56 followed by Control D, it doesn't notice that that's the end of the file. Okay, it's only if it's the first thing on a line. And we use this in other places. So if you use fgetC to read a single character from standard in, fgetC returns an integer normally, but if it hits end of file, it returns a special symbol EOF, which is actually -1. So Control D is not equal to EOF, it's not equal to null. It's just a way that we indicate that this is the end of our input. And code that pays attention to that, for example, the code in fgetC, the code in fgets will do something in response to that. Fgets will return a null. fgetC will return EOF, and so on. So we'll mess with that more when we do more input-output. Well, let's get back to debugging. So here's the code I want to debug. Let me throw some comments in here. All right, so want to debug gcc-o sort.c -g says include debugging information. And if I just run this with sort, it's just running it normally. Okay, but if I decide to debug this, I can say gdb sort. And now I'm sitting inside a debugger. So you get this big long welcome screen with like lots of licensing information that tells you it's free software. And the last line here should say reading symbols from whatever the name of your program is, and it'll say done. So if I don't put in that -g switch, and I say gdb sort, my last line says reading symbols from sort, no debugging symbols found. Okay, so I can still debug it, but it's not going to work very well because it doesn't know anything about my program. So make sure you use the G switch and then gdb sort. So I can say list and I can look at my program inside gdb. So list will show me 10 lines of my code. If I say list again, it will show me the next 10 lines of my program and so on. And usually if you hit enter, it just repeats your last command. So I can look at all my source code now. So I can list from line 1. All right, so gdb program name starts. You can say list to list the contents of your program. We can also say start, and start is how you begin debugging your program. So I'm going to say start, and it will tell you some stuff you don't have to worry about. But basically it's sitting here at line 7 of sort.c, which is this opening curly brace. Okay, it's the beginning of my main program. There's nothing executable up here. There's some prototyping of functions, there's some comments, there's a prototyping of a function that's declaring my main program, but none of this is sort of executable. So let's just list from line 7. And there's really nothing that's going to happen when it sees integer data 100, character buffer 120. There's no instructions that execute in response to that. That's just telling the compiler, I need 100 integers, I'm going to call it data. I need 120 characters, I'm going to call it buffer, and so on. And really nothing's going to happen until we get down here to line 12. Right, line 12 is going to set this variable size equal to 0. So I can print the value of the variable size right now, and it's negative 7672. All right, so we'll do a lot of prints. And most commands in GDB you can abbreviate as long as the abbreviation is unambiguous. The only command that starts with a P is print, so I can just say P instead of print, or I could say PR, and so on. So I can print data, and there's what my data array looks like right now. And it's got lots of random stuff in it, right? Presumably 100 numbers. I've never initialized it. So it's got random gibberish in it. And my string that I declared that I called buffer has got more random stuff in it. Starting with a 0, which occurs 24 times, and then a hex FF and some other stuff, and some more zeros, and a JUUUU, and so on. And it's just whatever happened to be in memory. So if my code started trying to do something with a data array, I would pretty quickly notice that the first number I was looking at was, 170 million or something. And I'd be like, wait a minute, where'd that come from? Okay. So this lets you see what's going on. And the first statement that's actually going to get executed is down here at line 12. Yes?
Is P the same as print?
Yes.
Okay.
And PR is the same as print. Oh, PR is ambiguous. Okay, I guess P is just a special shortcut. So P is for print. All right, so we want to tell our program to start executing instructions, and there's two ways we do this. We can say next, or we can say step. So next says execute until the following statement. So if we're at line 7 right now, next we'll say go ahead and execute until we get to line 8. Step basically says execute one statement. All right, what's the difference? The only difference is our current statement is a call to a function. If we say step, it will go ahead and it will execute that call and it will stop before it starts executing the first line of that function. So it's a step into, if you remember MPLAB in 270. A next will say, okay, we're about to execute a call. If I say next, it will do that call, it will do everything in that call, it will do the return, and it will stop at the following statement. Okay, so it's a step over.
If you step when you're doing scanf, would go into standard input.
Yeah, and it'll mess you up. So that's the trickiest part of this, is knowing when to step and when to next. Because if you accidentally step into something like printf or scanf, it starts complaining about things. So let's play with next. So I'll say next. Okay, so the next detail, GDB always shows you the instruction that is about to be executed. So I said next, it skipped over those variable declarations and it's showing me line 12, size equals 0. If I print the value of size, it hasn't changed yet because it hasn't done this instruction. It's about to do this instruction. So it shows you what is about to happen. And if I say next, and now I print the value of size, size is 0. Okay, that's good. And now it's about to do this printf statement. Okay, I don't want to debug printf. I want to step over that. So I'm going to say next. So it's made a call to printf. I don't have a new line at the end of printf though, so I don't actually see it. So this is a subtlety. When I run this program, I print out this message without putting a new line at the end, so that the last thing I see is a colon and my cursor stays there and I can type in a number next to it. But that can mess up your debugging. Because remember, when you print something, it doesn't always print. Sometimes it just goes into this pipeline, this buffer called standard out. And so this can look really weird because it's like, well, I asked it to print something, but it didn't print anything. So at this point, I'm going to control D out of here. I'm going to say quit anyway. I'm going to make a quick change to my code. I'm going to print a new line at the end. I'm going to recompile and I'm going to re-debug. And I'm going to say start, and I'm going to say next, and I'm going to print size, and we're right back where we were. Okay, so now we're about to execute the print statement. Let's say next. There's the output. Enter a number, control D when done. So I'm going to say next, and it's going to call fgets, which is going to wait for me to type something in. So I'll say next, and it's sitting here. Why? Because it's executing fgets. So I'll type in my number, 62. Now fgets has returned. And presumably it did not return null because I'm at line 15. Right, so this was the fgets that it just executed, and now it's about to do this. Okay, now we can look very carefully at what's about to happen. So let's see what this return from fgets was. What was this buffer? Let's print buffer, and you can see buffer is a 6.2 followed by a new line followed by a null terminator. That's your string. Buffer is 120 characters, so there's a lot of other stuff in there. But nothing is really going to care about that because right here in the fourth position we've got this null terminator. And so scanf, print, all that stuff won't really look beyond there. If you want to dig a little deeper into buffer, we can say something like print buffer bracket 0. It's the character 6. It's the value 54. That's the ASCII code for a 6. If we print buffer bracket 1, that's a 2, ASCII code 50. And if we print buffer bracket 2, that's our new line. So fgets always tacks a new line at the end when you hit enter. And then if we look at buffer bracket 3, it's a 0. We can look at size. Size is still a 0. And we're asking to scan buffer into element 0 of our data array. So let's print the data array again just to make sure, and it's got something crazy in the beginning. So we're at line 15 right now. Let's go ahead and execute this line of code, which is going to do the scanf. It's going to store the integer into data bracket size, and it's going to return some value. So let's just say next. And it's about to do this plus plus size, which comes after this, and this only happens if scanf returned a 1. So scanf evidently returned a 1. And size hasn't changed yet, right, because we haven't executed this plus plus. But if we print the data array, that first element is now 62. So the scanf did exactly what we wanted it to. It converted that buffer, that string, into a 62 and it stored it in that first position. And now if I say next, size has changed to 1. So now it wants another number, I'll put in 45. I'll do the scanf, I'll increment size. So now size is equal to 2 and my data array has 2 numbers in it.
So we can use side plus
Mhm.
plus side is
You can do either one. So this is a good sidebar node. What's the difference between these two things?
Increase the size after, or increase the size before.
Okay, after and before what?
What do you call it?
so you
Before you use it, right? Whether you're calling it or assigning it. So if we say something like x equals size plus plus or x equals plus plus size, the effect on size is exactly the same. Size gets incremented by 1. But this first statement will copy the current value of size to x and then increment size. This statement will first increment size and then copy it to x. So this sets x equal to size, this sets x equal to size plus 1. And both of them set size equal to size plus 1. So if all we're doing is trying to increment the value of size, doesn't make any difference if we do it before or after. So this is a useful screen to stare at a bit, right? My goal in writing this was that size would always tell me how many numbers I had in data, right? And I can see right now that at this point in my code, that's exactly what's going on. Size is 2 and I've got 2 numbers stored, right? Depending on how you write this, it might be your number of elements plus 1, it might be your number of elements minus 1, it might be your number of elements. So we can see that it's doing the right thing. Well, I want to type in 10 numbers, and that's a lot of interacting with GDB, right? So here's what I can do. I can use a command break. I can say break line number. And what that says is if I decide to tell this program to start running again, as opposed to stepping or nexting, it should run until it hits a line that I've set a break at. Okay, so this is a breakpoint MPLab. So this whole loop up here, I believe, is working correctly. I think it's getting input from me and scanning it and storing it in my array and incrementing size. So I want to just go through that until I hit Control D, and then I want to start looking when I get down here to line 20. So I'm going to say break 20. Okay, and it tells me it's at a breakpoint at line 20 in my file sort.c. And then I'm going to say continue. So I've got a breakpoint. I could keep stepping if I wanted to, but I'm just going to say continue, or C-O-N-T. So it wants another number, and it wants another number, and it wants some more numbers. And then I'm going to hit Control D when I'm done entering my numbers. And it flew through, got out of my while loop, came down here to line 20, and it's about to execute line 20, and so it stopped.
So continue continue is basically basically going into the program and executing.
Yeah, continue executing from wherever it is, and keep going until an error, until the program finishes, or until you hit a breakpoint, or a watch point, which we'll still talk about. Bless you. So now I can print out size. Size is equal to 7. I can print data, and there's my array of data, and it's in the order that I entered it in, and there's 7 numbers in there, right? Which makes sense because size is 7. And so now I can start saying next. So my next statement should print out data size and tell me that I got 7 things. So there it is, data size :7. And now I'm going to call my function sort. Okay, if I say next, it's going to execute that instruction, and it's going to not do anything until the next executable instruction, which is this for loop. In other words, this was a step over. So it called sort, it did all the code in sort, and then when it got to the next instruction after sort, which is this beginning of a for loop, that's when it came back and asked for my commands. So I missed all the action that happened inside sort, right, because I said next. So it basically did all of that stuff without allowing me to intercede. So I could print size and confirm that that's still 7, and I can print data and see that my data is sorted. But suppose that something went wrong. Suppose my data is not sorted, and I wanted to see what happened inside the sort routine. Okay. Well, it's too late at this point. Some debuggers, you can actually go backwards in time, which is kind of cool. But easiest thing to do, just go ahead and get out of here. So Control D says I want to quit. It almost always asks you if you still want to quit because something was running. Go ahead and say yes. Go back into GDB, say start. And if you remember, we wanted a breakpoint at line 20. I can say continue. I can put in my numbers. Hit a Control D. I'm at line 20. I can print my data. I can print size. I can see where I am, and I'm about to do my print statement. There's my print statement. I'm about to call sort. Now I'm going to say step. Okay. So everything we've been doing for the past 15 minutes, we just did that again in about 10 seconds, right? So the more you do this, the faster it becomes to work your way around here. At first, it's going to take a long time. You're going to want to make notes, and there's going to be missteps and so on and so forth. That's all good. So now I'm going to say step. And so I'm inside my sort routine. So I'm at line 33 of sort, so let's just list some code around here. So line 31 is where I declare sort, 32 is a bracket, 33 is the first executable statement. So I'm going to do a for loop with an outer variable and a for loop with an inner loop. So let's do some nexts. So I can look at inner, and that's a 0. I can look at nums, right? Nums was the first argument I passed to my sort routine. And if I print out nums, okay, so this is the next thing. So in my main program, I declare data to be an array of 100 integers. In my function sort, I said that nums is a pointer to an integer. Okay, we know that they're the same thing, but to GDB, it doesn't know that this is an array of 100 integers. Okay, just like the CPU doesn't know it's an array of 100 integers, it's just a pointer to an integer. So we kind of have to help it along. So if we say print the thing that nums points to, that's an integer. And it's our first integer.
So the thing it originally printed, is that like the memory location for that pointer?
Yes, that's exactly what it is. Okay, it's saying that nums is an array of integers starting at this location in memory. On a 32-bit machine, this is usually 8 characters. On a 64, it's 16 or 12. I can also say print nums bracket 1, print nums bracket 0, print nums bracket 2, and I can take apart my array like that and see my original data. So it's working on element 0. I can look at element 0 and element 1. And element 0 is less than 1, so it should not do this swap. So I can say next. And it skipped the swap. right? So it executed this if, it skipped the swap, which brought it down to this curly bracket, which goes back to the inner loop. So it's about to execute this next loop of the for loop. So inner is still 0. If I say next, I can confirm that inner got incremented to 1. And nums1 is not bigger than nums2, so it's going to skip the swap on that. So now inner is 2. So now nums2 and nums3 are out of order, so it should do the swap, right? So let's go ahead and say next, and it's down at line 36. So it's going to try to swap elements 2 and 3. Right, if I look at temp, it's uninitialized. But if I execute this instruction, temp is equal to that first number. And then if I do this, nums2 is equal to the second number, and then nums3 will get set equal to the first number that we saved in temp, and it did the swap correctly. So you go on like this, right? And big sheets of clean paper and patience and good music, and you work your way through your program, and eventually, if it's not doing the right thing in the end, you will find a place where it's doing something different, where it's trying to swap, but now both numbers are equal to 5 instead of actually swapping. And then you say, oh, something went wrong there. Well, maybe you have to go back and rerun it and stop and pay closer attention when you get to that point. But it's a process of creeping up to where the actual bug is and seeing what's actually going on. Once in a while, your program blows up and you run it in the debugger and it works perfectly. And that's horrible, right? That will happen once in a while. If that happens, you've got a memory issue somewhere. You've got an uninitialized value, or you've got a pointer that's pointing somewhere it shouldn't be, and it just so happens that when GDB is in the mix, it doesn't blow up. But when you don't have GDB, it blows up. And that's a harder one to find, but we'll talk about that another time. All right, so that's a quick overview of GDB. We'll be talking a lot more about this, and we'll be playing a lot more with it in the coming weeks.